First, I wanted to deliver my promise from Wednesday, when I hope that I gave you a bit of understanding in the context how you build up, what kind of algorithms you use to solve, well, quite simple problem really, but very complicated because of the way the universe is complicated and gravity is nonlinear. So now we are able to generate initial conditions for arbitrary cosmology. Well, not for arbitrary cosmology, for nonlinear for sure. But later you will see that if you want to do research about some model that just, let's say, vary slightly from CDM, not very exotic physics, let's say it's a different power spectrum of dark matter, not for baryons, so to say, because we observe them in CMB. Then you can do it. You can still generate initial conditions. Now you also understand more or less how to run and evolve this initial particle load that represents phase space of the dark matter and baryons together over the 14 millions of years of evolution. And more or less, I just touch upon this. We know, at least have the idea, how to find some stuff in the simulation, so we actually can make meaningful analysis like halos, and how to put galaxies and assign galaxies to halos and try to build some observations. Why? Because as I said, it's not only that you want to get some insight and see nice movies, how things swirl around together. You want to do science, and we're doing science. We do physics here, which means the observations is our final jury. If you do something not comparable observation, this is really theoretical physics, but even sometimes a bit touching on philosophy. So today I will show you, and I'll tell you something about the dark matter, because as I said, I think you didn't have a separate lecture just on about dark matter in the program, so it will be just half an hour we're going to spend me reintroducing the idea and giving you basic, and then the remaining part I will try to show you step by step our way of thinking, where we did some research about testing the different dark matter candidates and how you can set up a hypothesis and model testing using simulations, and how you can learn something about the different dark matter models and what our universe admits this way. Okay, well, lambda CDM, our beautiful standard model of cosmology. Again, for some people I think it's ugly because it's very phenomenological, but nonetheless it's very successful. I think we should be proud of this. I said this already on Wednesday. But there's a huge price, right? Because if you look at the pie chart, you see that all these components of the universe that we add to the energy momentum tensor to kind of have a chance to match the observations have this adjective dark to it. Dark means like dark energy or dark matter, but really just encapsulates our ignorance. It's a bit frustrating that 95% of energy density of the universe is in some kind of a form of either energy or matter that we have a very bleak idea about. We probably know what kind of a properties it cannot possess to pass observation, but nobody captured the dark matter particle yet, and the dark energy, whether it would be Einstein, in cosmological constant or other thing, it's still just it has no issues on theory level. So, cosmic pi, why? We'll be talking about these pieces of the pie, just a little bit, of around 30% of energy density, according to the recent CMB measurements. So let me just reiterate for you some classical arguments for dark matter, why we actually need this, and then I will follow immediately with really modern, robust, and much more powerful, I think, cosmological-based arguments in favor of the dark matter. So dark matter, what it is, it will be hopefully apparent for us, at least on the theoretical level, soon. What it is exactly, we still don't know, because we don't have a final strong evidence for a particle dark matter. But we know there's a need of such a substance if you want to really keep the laws of the universe as we know it, mostly the law of gravity, but not only, and understand the observations we have. It started from the nearby universe, when you have the observations of the, for example, velocity dispersion of the galaxy members of the Coma cluster. There you have a Coma cluster, and then next to the Coma cluster you have a histogram of the velocities, line of sight velocities, of course, which you can measure just, you know, if you measure redshifts and then assume that you don't have many interlopers, so all the galaxies you see in this part of the sky belongs to the Coma cluster. You find the median redshift and assign this to be the center of the cluster, or maybe you find the brightest cluster galaxy, which sits in the center and takes its redshift. Then, using the small differences in the redshift of the members, you can derive the line of sight components of the velocities. And this is what you get when you got the distribution of it. This is what Fritz Zwicky got also already in 40s in the last century. And if you believe the clusters are to be meant to be relaxed systems, means they're not collapsing or not dispersing, right? They collapse the equilibrium, then you can apply real theorem to this to such an object. And this means you can evaluate or equate the average kinetic energy, which is described by basically the dispersion of the velocity here measured, to the bounding energy, which is a gravitational energy. And Fritz Zwicky did that, and he got that there should be 25 times, at least 25 times more gravitating matter, gravitating energy, to explain such a big velocity dispersion. Then, of course, all the clusters start to showing the same stuff. And then we move on also to 70s, where Rubin and Ford, who had on their hands amazing apparatus for that period of time, which was the spectrometer that could actually measure lines in the radial frequencies. And they were able, for the first time in the early 70s, to measure rotation curves of galaxies beyond the disk, basically using the H-alpha lines from the hydrogen. And that's a classical measurement of the so-called galaxy rotation curve. And you have it here on the bottom panel. So R is the radius from the galaxy, from the center, V is the velocity. As measured, it's not so simple to infer this velocity. Of course, we don't observe full 3D velocity, it's only one component. And then you need to assume some kind of a G's analysis to assume how the orbits are distributed. But you can do this, and assuming there's some relaxed circular velocity at this distance, this velocity that is plotted here, measurement, it would be the circular velocity on the circular orbit at this distance, equivalent. And then you have clearly, you see the discrepancy. The data favors much higher velocity, but it shows the velocity is much higher than what you would expect if you would just count the gravity and the really simple law for the circular velocity from the luminous matter. Well, these are classical arguments, right? So there was a growing evidence from the last century observations that there's this stuff in the local universe, at least, at the scale of galaxy clusters and on the scale of the spiral galaxies themselves. Later we also get the argument for the elliptical galaxies, because they have they don't have a rotation, coherent rotation, but the velocity structure is the dispersion is supported. But you can also measure the average dispersion velocity of stellar component, stellar spheroid in an elliptical galaxy, and also connect it to the gravity, and also you want to match the budget. So either you modify gravity, but then you see that it doesn't work for the whole universe, you completely break down the expansion history and things like that. Well, you know, I won't gonna spend more than one sentence about the modified Newtonian dynamics. That was an attempt to fix the problem of the rotation curves of the galaxies, but in my opinion, it's not a cosmological theory. It doesn't have a proper background treatment, so it's even worse than Freeman-Robinson-Walker that assumes that the universe is flat everywhere, even though we know the local is not. So put this aside. If you like Mont, you will know much more about it than me. If you don't, then, well, just follow me. I'm not Mondian. So also there's some argument that is growing. If you start counting the luminous matter in the local universe and use something light to mass ratio, mass to light ratio, basically you assume some standard relation of luminosity to stellar mass. So basically, you can model this by assuming some star population, you know how much light, how many old stars, how many big stars, small stars you have, so you can convert. It's always, of course, just the average relation with some scatter, volumetric luminosity to the stellar mass. If you do this and start playing this game, you'll see that, you know, observing also in the local universe, you will have this lack of the missing matter problem. So it's just not just the in the galaxies themselves, but also in the local universe. So it would seem that we are the special jellies in the big jar. The only very special because we are just on the surface. We are made by luminous matter. Luminous means you don't need to shine, but it is enough to absorb or refract light to be detected. And the rest is somehow something mysterious. Okay, now usually most of the dark matter classical talks would just briefly mention the classical arguments and not so much go into the details about the modern arguments. At least I've seen some talks like that. And I think it's very important to understand that these classical arguments, very important, they play a role, they gave us hints, but nowadays, we live in the precision cosmology era, and we have much more statistically significant and stronger evidence for dark matter than this early pioneering work of the Fritz Zwicky and Vera Rubin. More than just observing locally what happens in galaxy cluster. We have the high redshift universe evidence, intermediate redshift evidence, low redshift evidence for dark matter. And one of the very powerful ones is the famous bullet cluster. You might have heard about it. It's a low redshift observation. It's a pair of colliding galaxy clusters that we see the collision basically face on. And then here you have a map when the green contours are the potential lines of the inferred gravitational potential, how the gravitational potential was inferred. Basically, this galaxy cluster is so massive that it acts as a strong gravitational lens. It's bending the time-space around it. And fortunately, behind this galaxy cluster, there are plenty of small, weak galaxies that act as a kind of a screen casting light through that lens. So we can apply the weak lensing analysis, very careful analysis, and infer by looking how the matter distribution in galaxy cluster distorts the lights of the background galaxies, where are the centers of the potential. So you have these green lines, and I put these two ellipses to emphasize where are the centers of the potential, the two strong centers of the mass. Now, you have another interesting component of this object, which is a very hot gas that emit X-rays. And then you see here in this intensity map, from the blue through red to yellow. And here, the center, the highest density and highest temperature is here at this very center of this system, not where the center of the gravity is. And how you can understand this? Well, the stars and galaxies basically inside clusters. Stars are inside galaxies, and the galaxies inside clusters act as a collisionist particles. I mean, of course, galaxies collide, but on the scale of clusters, this happens very rarely, right? The galaxies can fly through each other very easily. On the other hand, you have an intergalactic, intercluster low-density gas. It is collisional. So basically, if you hit these two clouds of gas with the high impact velocities, the gas will shock hit. This is just standard hydrodynamics. And if it's shock hit, you will have that's why it's called bullet cluster, because if I remove this one line, you see this part here. It looks like a classical bow shock that is created when you have a high velocity projectile traveling through the gaseous medium. So the gas stayed in the center because it was heated. So gas was collisional, but the rest of the gravity just fly through. So there must be some component that's completely collisionless. And of course, you can't explain the contours with just the mass of the galaxies. You need a huge amount of dark matter. By the way, exactly that, more or less that amount of dark matter that you would need inferred from the CMB. Okay, let's move on. So another interesting, very growing evidence is from the so many observations we have of galaxy clusters, and you can connect especially observation of the hot gas, X-ray corona emitting gas from galaxy cluster. So if you assume that the galaxy clusters are in equilibrium, which I already did from the Zwicky time, it's not only that the velocity of the galaxies are corresponding to the mutual bounding potential energy, but also if the gas is not escaping the cluster, it has to be with thermostatic equilibrium with the rest of the cluster. So basically, if you write simple equation, this is something using just Boyle law and the gravity bound energy, you're going to get that profiles of the temperature and the density depends on the profile of the, are fed by the profile of the inside matter distribution. And if you do the careful analysis for most of the galaxy cluster we have observed so far, for which we could observe this hot X-ray corona with the good precision, and for which we could really also connect all the galaxies, we get again that there's at least factor of 20 of missing gravitational energy, factor of 20 missing mass. And this is really for all clusters for which we could really observe X-rays. There is some problem with some of the clusters that have a cool cores, but this is not a cluster talk, so I'm not going to go into details. But it is just more than Coma or Vigo cluster. Nearly every cluster, galaxy cluster in the universe that we can observe X-ray shows that the bounding energy is much higher than what you can really account for the visible matter. Finally, we also have a very interesting local evidence that, okay, you could believe that there's this dark matter, but maybe it's just some kind of a baryonic debris, that some brown dwarfs that never make stars, that will be too tiny to see them in the galaxy clusters and too tiny to see them in the distant galaxies, but there will be so many of those baryonic debris, asteroids, planets, dwarf planets, brown dwarfs, that you still make up the dark matter halos. Well, locally, we measured this that using the Milky Way and Warsaw University of Astronomers play also a crucial role with this one of the longest running experiment in astronomy, optical galaxy lens experiment. They provide very strong evidence that the dark matter cannot be baryonic, at least definitely not in our galaxy. And we believe that our galaxy is not very special. This argument would also apply to the remaining galaxies. The idea is very simple. It comes from the Bogdan Paczynski, a late, also very famous Polish cosmologist and astrophysicist. The idea was that, okay, we sit in the Milky Way in a disk. Let's find nearby galaxy. We have plenty of stars, and there's Magellanic clouds or galaxies like that. And let's monitor as many as we can stars in this nearby Magellanic cloud. And because we observe so many stars, even if some events are rare, we'll be able to see these events from time to time. And what are the rare events that you're looking for? These are called microgravitational lensing events. So whenever you have a compact body from our own galaxy, from the disk or from the halo, that just flies through and cuts the line of sight between you, right, which you are here, and the faraway star, you're gonna should observe deviation in the light curve of this distant star caused by the gravitational lensing, and this should be compact. If you have extended objects, they will be just a little bit obscuring. It wouldn't be so strong. It has to be compact objects. So black holes or lots of this debris. Like if there will be plenty of invisible debris because they couldn't shine, like never made it stars or planets, they should promote this gravitational lensing. And after 20 of years observations, the Ogle experiment, and before Ogle there was also other experiments like that, Nacho, among others, could confirm that not more than 10% with the high fidelity, not more than 10% of the mass of the Milky Way halo in dark matter can be in the form of this baryonic debris. So at least remaining 90% should be non-baryonic dark matter. At least the dark matter that wouldn't make this lensing experiments. Finally, I think the most powerful, at least statistically powerful argument for the dark matter, for non-baryonic dark matter, comes from the early universe, from the CMB itself. So you heard a lot about the CMB during this school, and of course you heard also about acoustic peaks. So I'm going to be brief here. So we take the CMB, which supposed to be the fluctuations coming from the inflation, if you believe in the hypothesis of inflation, and you plot the angular temperature anisotropy power spectrum. You see the series of peaks, right? And the peaks have a special meaning. And the position and the relation of one peak to the other can tell you a lot about the composition of the early universe, in which this plasma and photons oscillate, and they were emitted, so we observe it today. So imagine that we have this fluctuation from inflations, and the universe expands, grows as full of plasma, and until recombination, all the photons and baryons are coupled together to the Thomson scattering. So basically you don't have two separate radiation, photon and baryons, you have just plasma, photon baryon fluid, we call it. So basically they mutually interact with each other all the time. On top of this, if you have a dark matter, you still have a dark matter, but of course dark matter is not coupled to photons if it's not baryonic dark matter, because non-baryonic dark matter doesn't shine, doesn't reflect, doesn't absorb, and doesn't emit the light. So you cannot have any coupling to radiation. So now you have this fluctuation that was, universe was growing, that was having a little bit of the extra rational potential. There was positive density fluctuation from inflation, so it attracts the stuff from vicinity. So basically you have gravity starts compressing the plasma. So you can think about this, you have an effective mass, this is the gravity, that falls into the potential well. But as the density increases, then of course pressure builds up inside, and eventually the pressure will be so high that it will resist the gravity. And then of course it will start decompress. So that's why you have a series of these peaks, because more or less it's harmonic oscillation, because baryon photon fluid is compressed in the dense potential well, but then it decompresses because of the buildup of the pressure. So first peak is just a compression, first inflow into potential well. Now you have a second peak, and it comes from the rarefaction. What it means? Well, as I said, once you heat up the plasma, the pressure grows up, radiation pressure, it starts to winning against the gravity, and you have a rarefaction, so a bit of decompression. But what was decompressed, what can be decompressed is only those particles, those elements that can feel the radiation pressure, so no dark matter. So the difference between these two peaks, I already tell you that there was a huge amount of stuff that never got decompressed. And finally, the third peak is the compression in potential hills, because once you expel the matter baryons fluid because of the growing pressure from the potential hill, you have two nearby fluctuation. Imagine you have something like that. In 1D, everything looks much nicer, of course, right? A very simple fluctuation, right? So you compress here matter first, then the pressure builds up, and then of course it's decompressed, it starts being pushed outside of the density peaks, and then you start to squeeze the matter again here, what was originally under density. So this would be raw. If I would plot this as a potential phi, I would have to change, right? Because whenever there is a potential here, you have an overdensity, whether the potential here you have underdensity, so on and so forth. But this is very simple physics, and it's very powerful because it's a very, very precise measurement from the early universe. So if you do these calculations, the relative positions of the peaks, of the first peak especially, depends on the acoustic horizon, so basically it depends on the size of the universe under recombination, more or less. But the relative positions or amplitude of the peaks tell you a lot about the fraction of the baryonic to non-baryonic dark matter. And because the first peak is so much bigger than the second peak, it tells you that you have at least around 6 times more non-baryonic dark matter already there in the 1100 redshift universe than baryonic matter. And if you wonder how statistically significant it is to find to find by chance match like this to the data without dark matter would be a 40 sigma event. So now finally we have a big sigma, so we can give it to particle physicists that complain that we have only 3 sigmas hints in astronomy. No, 40 sigma in CMB, 40 sigma detection of non-baryonic dark matter. So, and of course there are a couple of nice extra animation from the Wayne Hugh from the University of Chicago, and the animation don't work. Well, this was just to show you that the peaks also respond to the amount of the dark energy, but this is not important for the argument I want to make. So, we have a minimum 6 parameter lambda CDM, you know, I never corrected this plot for sharpness because at first made this slide many years ago when every few years you have another WMAP or Planck data release and you have to change the numbers all the time. So it's better like this. There's some numbers we know that the 6 parameters, amount of the non-relativistic baryonic matter, amount of the total non-relativistic matter in the universe, optical depth to the last scattering, size of the acoustic horizon. This is something slope, NS, slope of the primordial power spectrum, and this is just the amplitude of the primordial power spectrum. This AS, this is A here, can be related to sigma 8. So these are 6 parameters that can give you this amazing peak to CMB. But you know, from this, you definitely know to introduce this dark matter, and you cannot get away with that. So this is what I've said already, being conscious of time. And last but not least, for me also a very appealing argument that came from Jim Peebles. And I think many other things that for he was given the Nobel Prize, this is one of the very important contributions. This is just a very, very scrutinized version of the argument. So basically, if you plot how the different component densities can grow, perturbation of the densities can grow in the universe, you basically in the different epochs, radiation, matter dominance, and dark energy dominance, this is what you get. So first you have the radiation dominance that completely, there's no chance that you will grow any perturbation in the matter, and the baryonic matter and radiation, because the matter and radiation is coupled, so you can only oscillate at best. But then in dark matter, because it's not coupled, as soon as you start to becoming less and less relativistic universe, so you move towards the important period when it's called matter radiation equality epoch, this is TX, the dark matter perturbation can start to slowly grow. Only logarithmically, nonetheless they grow. And this, you will see that this tiny initial growth was very important. Then you pass the matter radiation equality, which marked the transition to so-called matter dominance era. Here, before the recombination, you still cannot grow any density perturbation in baryons because they still coupled to photons. But now, the perturbations in dark matter can grow very efficiently. It's just a simple power law, which means that as soon as the universe passes to recombination, you already build up a sizable growth of the density perturbation in dark matter. So this is a combination. So quickly baryons can follow, falling into the potential where they are already there in dark matter. If not for this effect, if there wouldn't be this growth in dark matter, which is not coupled to baryons, in this short amount of time, because you know this is redshift 3000, this is redshift 1100, so this is at best 100,000 years or something like that. You wouldn't start here with the perturbation, but probably somewhere here. This means that you would go from 10 to minus 5 in CMB to 10 to minus 2 now, right? So there will be not this classroom, there will be just the diluted gas with the density contrast of 1% at best. But thanks to this tiny boost, it looks right, but thanks to this the boost to the dark matter, we can actually, using only gravity, get from 10 to minus 5 in CMB to millions today, like you see in the density contrast in the galaxy cluster. So without the dark matter, you wouldn't have hospitable universe. Hospitable in the sense that if you like to live in a galaxy, on a planet, you have to have dark matter. Okay, it took me half an hour, I think, to recall, from my perspective, most important arguments. Let's see. Yeah, so you have it here. Okay, it was 10 to minus 3, so you would get to 10 to minus 3 even worse. 10 to minus 3 not to pain, 10 to minus 2 without the dark matter. And yet we get in the linear perturbation theory to 1, and even more in the nonlinear regime. Okay, so what is this dark matter, right? We know that we need to add dark matter. We know what dark matter cannot be. It cannot be baryons. It can be some kind of a not shining cold baryon nuggets of asteroids, planets. Because in CMB this would be seen. And also, Hubble experiment also showed. So it has to be some kind of exotic particle that only interacts with gravity and maybe at best weakly forces, because you cannot have a strong nuclear interaction because we would already detect it in the Earth-based laboratories. So don't read all these names here. The idea of the slide is to show you that particle physicists are very potent and creative people, so they never suffer for the lack of ideas. So immediately as the field started growing, they came with all these possible ideas. Oh, dark matter could be this, dark matter could be that, Higino, some scalar dark matter, some supergravity, supersymmetry, everything. They can come with everything. So for me as an astrophysicist and cosmologist to take every single model, try to work out the math, put this into my computer, and try to learn, okay, which of this model makes sense and produce realistic universe is completely impossible. There will be you would run out of the PhD students, postdocs, and professors in the millennia to do this, because they are very potent. So until we have a solid candidate from the particle physics that is not only plausible theoretically, but have some root in the observations, the next best thing we can do is to treat the dark matter phenomenologically, and this is what we do. So we say, okay, we know more or less what dark matter is supposed to do. Let's say we don't know exactly what the particle it is, and we just gonna play in dark, assume what we know about dark matter, put this kind of stuff in simulation and see what happens. So phenomenologically, you can divide dark matter candidates of this particle into different categories based on one very simple criteria. So this will be a tale about the good, the bad, and the ugly, which was missing at the end. So it can be hot. It can be, which means the particles are light. Particles, if the dark matter was produced in the real universe, just after inflation, in some kind of equilibrium process, this means they are thermal relic. And thermal relic retains some of the kinetic energy from the time it was created, and this depends on if it is made by light particle, I'm talking about the rest mass of the particle, or not. So light particles would make hot dark matter. I will explain in a moment what this means. You can have medium sized dark matter, which we call warm dark matter, and this EeV, KeV, this is the approximate mass range of the rest mass of the particle that makes up the dark matter. I don't know why I pick up tomatoes, I just like tomatoes, I think it's a medium weight here. And you can have cold dark matter candidates. This would be a very massive particles. Presently, in the lambda CDM we have a cold dark matter, and this would be a particle. The best candidate was weak particle. That thing is some kind of coming from supersymmetry. It's a Higgsino and Photino. They have this. It's actually a very mixed state of some of the particle particles from the supersymmetry. Nonetheless, it should be a very heavy particle. So the connection to the temperature is, of course, by no means doesn't mean thermodynamical temperature. If I would give you a thermometer and a bucket of dark matter, you stick the thermometer, it wouldn't tell you the temperature of dark matter, of course, because it doesn't interact with that. What we mean here, more or less, is that, okay, we understand thermodynamically what would happen to the cloud of the gas of similar particles if they would be massive, light, or medium. So basically, hot dark matter particle retains high velocities from the early on, which means it cannot cluster on the small scales because it has this internal energy. It means the particles stream away from small scale perturbation, and this is like clouds. Now the medium mass can collapse and condense on smaller scales, but still have some internal energy, much higher than the cold part, which means that there's also a limit to amount of the limit on what scales these things can condense. And finally, cold dark matter particles retain very little internal velocities, kinetic energy from the early universe, so it can really condense and collapse nearly on all scales. Just to tell you what's the difference, cold dark matter particles should have nowadays remnant velocities of the order of meters per second, maybe 20 meters per second, something like that. Warm dark matter, it would be hundreds of meters per second. While hot dark matter is relativistic, so it's like neutrinos. So it will be thousands of kilometers per second. And I can use this very simple division to try to emphasize, imagine what this kind of a particle would do to the structure formation. And this is where I'm going, and this is when I'm going to try to show you how we approach this, trying to learn between different models and what is possible in our universe and which model is not possible in our universe. The idea is that we don't want to find a proof. Yeah, this is the dark matter particle. We solve the problem. No, we want to find hints and constraints from observation and give it to our colleagues from particle physics and tell them, forget about this model, maybe you should focus about this model because only this part of your phenological models of the dark matter can really pass the observational test. So we can implement such properties like the mass of the, or type of the dark matter particle in the simulation, and you will have different striking differences of the structures you can form. So this is forget about the text maybe for the sec. We're just going to run the same initial conditions, but we change the initial power spectrum. And then this initial power spectrum tells you on which scales you have some density perturbation. So of course from inflation all scales have scale-free nearly perturbation, but then this physics of dark matter tells us that hot dark matter completely wipe out the small scale perturbations, and then you see, you form maybe large scale structure looks like this is early universe, and this is this from this kind of a bundle of the fixed spaghetti you create this halo. Warm dark matter you have many more fluctuations, but not that many as in cold dark matter, and you create this halo, and in cold dark matter you have fluctuations on all the scales nearly down to the Earth size nowadays. Dark matter halo. So cold dark matter predicts that there should be dark matter halos that will have 10 to minus 6 solar masses. And this is the 10 to the 12 Milky Way-like halo that you might expect to create in the universe if the dark matter is cold, warm, and hot. So obviously you see some striking differences. There are many fewer small specks in which you normally would think there will be satellites, and this can be related to something we call the streaming, free streaming scale. It's just basically if the dark matter is the thermal relic, it's inversely proportional to the rest mass of the dark matter particle. So, what can be known by baryonic dark matter? This is some kind of a candidate that, as I said, we don't want to dwell into this, but we want to have this idea that, okay, we investigate warm dark matter, and if theorists will tell us, no, there's no way to have the warm dark matter in the universe, at least not standard model doesn't admit for this, so it would be stupid to run simulation. So they need to have some ideas what kind of particles could be in these categories. But as I said, theorists are very important and they provide us with many ideas. So for hot, you can have neutrinos. And by the way, neutrinos exist. This is what we know, right? Fermi got the Nobel Prize for among others, also for neutrinos. And neutrinos have mass. We also know this now. So neutrinos, by the way, is the only dark matter that we have full evidence that exists in our universe. Unfortunately, as you remember lecture from Wednesday, they cannot make up the majority of the dark matter because the universe that would be made of hot dark matter from neutrinos wouldn't be compatible with the galaxy clustering. So we know that the hot is incompatible with the last structure, but also with the CMB, because there's not enough neutrinos, or neutrinos are too light to explain this the whole dark matter. Nonetheless, they provide few percent of this energy, few percent effect on large scales. Okay. Now, for one dark matter, there's a very nice candidate that comes from the minimum extension of the standard model. It's called stellar neutrino, and it will have a mass from keV to from kilo to mega electronvolts. And for cold dark matter, you can have axion or neutralino. By the way, just making a quick comment, these are still candidates that are in game, even though axions have problems. But I told you in a moment that, well, the cold dark matter needs to be very, very massive. Yet the axion has 10 to minus 5 at least electronvolts. So something doesn't seems right here. Well, axions are very special because axions are not produced as a thermal relic. They are produced as a chemical freeze-out. So it means the rest mass is not imprinted in the free streaming scale. So they are natural cold dark matter candidate. Nonetheless, they are very light. But there are different kind of particles. There are scalar particles. But, well, they should give you similar fluctuations as in cold dark matter. One big distinction, both stellar neutrinos and neutralino are fermions. Axion is a boson particle. So it means If the dark matter is made of bosonic particles, you have a problem because you cannot just solve Wasser's equation anymore. This will be stand for Boltzmann collisionless fluid, which will be fermionic. You also need to solve like Schrödinger-like equation, because then you have a bosonic dark matter that can have this bond states, solitones, and oscillations that comes from the interference. So how we should set up the experiments and simulation to try to test between warm and cold dark matter, for example. Before I get there, I'm just going to mention maybe in passing that these candidates that are put forward to this dark matter, broad candidates, even though we approach phonologically, predict that there could be a chance to have some kind of an indirect detection from astronomical observations, because they should provide some time. They have a portal, as the particle physicists call it, to the standard model. So if there's a cold dark matter that is made of the WIMP-like particle, and it's Majorana fermion, this means that this particle will be its own antiparticle. So you can have two dark matter particles when it's very, very dense part of the universe. They can scatter sometimes, collide, and they will produce, they will annihilate together. And then by annihilating and producing huge energetic boost of radiation, they can cascadely, decay to some antimatter neutrinos and mostly gamma rays. So if there's a cold dark matter, and if the particle of cold dark matter is made by WIMP-like particle, the prediction from theory is that there should be some dark matter self-annihilation, and there should be gamma rays coming from the very high density regions of dark matter. In the warm dark matter case, we have the stellar neutrino, which is the semi-stable particle, although its lifetime is comparable to the Hubble time. Nonetheless, it can decay, and while it will decay, it will produce photons in the X-ray range. So this is additional distinction, because on top of the effects we can expect the dark matter candidates will make on the structure formation, like galaxy structure formation, there's additional channel in which we can try to get some information from observation if we can predict what kind of signals should we get from X-rays, or from gamma rays, if this will be this dark matter particle candidates. And then you go to observation, you see absolutely no signal like that, and maybe you can falsify some of this physics. And interestingly, there will be claims from different groups that both kinds of these signals were actually detected. There are claims that, for example, in our galaxy, this excess gamma ray coming from the center of the Milky Way that normally cannot be accounted for anything else, so might be gamma ray from the dark matter annihilation. And there are different claims that from some nearby galaxies and nearby galaxy clusters, Perseus and Andromeda, Perseus clusters, there's this X-ray emission of 3.5 keV X-ray line that cannot be attributed to anything normally we would attribute with the stellar astronomy. That would naturally come from the very favorite warm dark matter stellar neutrino. This is just to show you that this is Fermi satellite data looking at the very center of our galaxy, and you have some known pulsars here. And if you remove all the known sources, you're left with this resonant picture. And this could be a signature. I say could be, because if we were certain that it's a signature of the dark matter annihilation, I wouldn't spend time of investigating warm dark matter. Unfortunately, this is not so solid evidence, because there's a high probability that in our very center of our galaxy, there's this unresolved nebula, cluster of neutron stars that will produce by the synchrotron emission gamma rays. But pulsar, they wouldn't be pulsars, they would just be neutron stars mostly. And of course, they are too far away, they are too small to be resolved. Nonetheless, they would provide more or less this kind of a signature as well. So because we don't know how many pulsars and neutron stars they are, and we don't know what's the portion of the signal coming from dark matter, if any, and what's the portion of the signal coming from the astrophysical sources. And similarly, there was this claim by Alex Boyarsky group that they identified this 3.5 keV X-ray line, and they stacked some clusters, and they stacked some galaxy clusters, stacked some also later the observation of Andromeda galaxy. and you see apparently there's a line here. I mean, maybe there's something here. And remember, this is just the residuals from the feed without the line, and then you see that maybe there's some evidence. But given the error bars and the analysis is very hard to make it, it's a hint, right? We would say 2.2 sigmas maybe hint. There might be something. Well, it's good enough for me to investigate and run big simulations to try to see if there would be cold in warm dark matter, what else we can learn from our local universe. And some people would say that's rather unlikely that the both groups can be true and both dark matters are right at the same time. I make an important comment here. Nature has absolutely no obligation to play a clear game with us, to be fair. Nature cheats all the time, like in poker. I mean, it is us who wants to have things simple. But nothing prevents nature to produce 2, 3, 4, 5 different kinds of dark matter made of different particles with exotic physics. And this would make, of course, this investigation much harder. Although it's not so bad, because it's not bad science to operate under assumption that there's only one dark matter particle. Look for a kind of a signatures you will have for this or different kind of the dark matter particle. Until and unless some observation forces us to abandon this approach. So, we cannot really, there's always an infinite amount of things that doesn't exist and compared to things that exist. So obviously you cannot just keep going and try to falsify things that doesn't exist if they don't exist. It's insane. So we're gonna focus here on trying to, building a simulation that will allow us to get some interesting information about how differently we can distinguish between these two scenarios, between warm and cold dark matter. So the thing is that, as I said, these dark matter models differ in the free streaming length, which means they differ in the scale at which the perturbation stops to be appearing. And the scales of perturbations is measured by power spectrum, right? We know this, we discussed this previously. And here you have observations, some of the power spectrum from the CMB on very large scales and some galaxy clustering. And this is the co-moving wave number. So you can get from CMB. Of course, it's a CMB that is interpolated to present day, and so on and so forth. So basically, the black line is the lambda CDM prediction. The problem here is that the warm dark matter particle would predict this damping of the power spectrum already on very small scales. So this is some free streaming, you can make simple math. So reasonable warm dark matter predicts that the fluctuations below 10 to the 9, 10 to the 8 solar masses, I mean already tell you in the Jeans mass, should be damped, should be suppressed, while cold dark matter can create perturbations all the way down to 10 to minus 6 solar masses. The problem is that the place in which of the power spectrum, scales at which these two models differ very significantly, is already on subgalactic scales, which means a very strong and nonlinear regime. So you cannot just use these observations to distinguish between the dark matter, right? Remember, this is the real data and Mo galaxy catalog from the cold dark matter simulations. So, both warm and cold dark matter will produce the same large-scale structure universe, while the implication for particle physics will be very, very different. So we need to go to small scales, to dwarf galaxies, and even smaller, to try to see for some differences between them. Again, we can do this thanks to simulations. So it was like 10 years ago when we were discussing how we could, try to attack this problem. Of course, it's not that before that there were not studies about warm dark matter. Warm dark matter exists in astronomy and cosmology for quite a long time. But now we have a strong candidate with 3.5 keV stellar neutrino, because other lighter warm dark matter particles were already falsified by high redshift observation of our universe. So we had some strong contenders. Cold dark matter, everybody knows and loves or hate, and some very strong warm dark matter, motivated actually by the minimum extension of the standard model for elementary particle. If you haven't heard about this minimum extension model, it not only predicts the warm dark matter candidate like stellar neutrino, but also explains the stellar neutrino oscillations and neutrino masses. So it's a quite interesting intellectual model. So we thought, okay, The best thing we have for observation is our local group, and even better, our Milky Way and its satellites. So if we have two dark matter models that differs only on those small scales, let's try to come up with simulations that would give us a reasonable amount of the Milky Way like analogs, so we can make a statistics, right? So we need at the same time high resolution, go to the, we have to be able to resolve small halos that in which galaxy would live, but we need to have also many realization of such system to build ensemble average to be able to combat the cosmic virus. So we came up with this Copernicus complexio simulation. Copernicus complexio because it means the Copernicus conundrum, right? It's going back to the Copernicus principle, saying that we're not privileged in the way we observe the universe, and this means we wanted to have at least around 50 well-resolved halos with high resolution that would correspond to dark matter halos of the Milky Way. In able to do this and afford this in computer time, you cannot do this whole box with the same number of particles because you run into the problems I discussed on Wednesday. So we came up with this zooming solution, which is called compromise. You put high resolution sphere in a much bigger box, and in this high resolution sphere you have, you have dark matter particles of the very small mass, and you surround them with the coarse particles, the medium resolution and very low resolution. You're not interested in this part. This is not really physical. Well, they will be very, very big halos only because the particle mass is huge here. Nonetheless, you need to keep it so all the tidal forces, all the gravity and large-scale structure influence inside this high resolution is right. But you only measure and not interested in the object that you find in the zooming region. So this is reasonable compromise that with only something like 10 billion of particles can give you this 36,000 co-moving megaparsec high resolution volume with the resolution of the mass just like 10 to 5 and the force resolution of an order 200 parsecs. So it can really go to the small scales. And we did it with the cold and warm. And we decided let's do some tests and try to falsify one of these models. But let's see what the local observation tells us. So this is the poor man's movie. Unfortunately, I lost the original animation, so I'm going to show you this in the slides. So this will be assembly of Milky Way halo from our simulations in two models, cold and warm. So this is what you see at redshift 10. In one dark matter, you see this kind of acoustic things because you have much easier collapse of the Zeldovich pancakes and filaments because there's not so much granular stuff that basically interacts. So you see, this looks really much like a pattern when you see on the light on the bottom of the swimming pool on the sunny day. Now you move with redshift, you start to collapse more. Redshift 6, redshift 1, you have already two big halos and some few smallers. And finally, by redshift 0, you assemble halo that has 10 to the 12 solar masses. So if there would be Milky Way inside, we should be the same halo, the same galaxies. Yet you see, of course, the number of small specks is different. Although some big satellites are in the same, more or less the same, not really exactly the same places because the orbits become nonlinear, but they have similar properties. But this model predicts there should be much, of course, more smaller specks. So obviously we know that in this small subhalos, as I told them, we should expect that Milky Way satellite galaxies should live. So let's count them, right? There was a question about missing satellite. They will see, I'm going to get back to missing satellite. So we do, and of course we observe the Milky Way satellites as beautiful dwarf galaxies. Now, thanks to dark energy survey and other surveys of the sky, we know at least like 50 very faint satellites, but there's only around 20, 15 quite bright ones, including some classical like Sagittarius, Sculptor, Carina, Fornax. And of course, this is the way outdated plot of the local group of the Milky Way satellite system. Because if I would put this something up to date, we'll be swarming with small satellites. And of course, this is dark matter only, and I already mentioned that it's not so easy to make a galaxy in our universe. This is because of the re-ionization. And it's not so simple to say, okay, I'm gonna do abundance magic, and I'm gonna take one satellite Milky Way and put this in the halo here and there, because if you do this for these two models, you will never run out of halos. So the problem is that you have to implement some kind of a physics connection to put the galaxies in the dark matter only simulation, because on those scales the physics of galaxy formation is very important. So what we did, we followed the semi-analytical model of galaxy formation. which implements all of these processes that I briefly explained on Wednesday. And this model, this was Durham galaxy formation model, and I think particularly for this project I'm gonna make it was Violeta Gonzalez Perez model. By the way, there's a model like that with the full Millennium simulation galaxy catalog that you can download for free from Millennium database and check the properties. It predicts, volumetric luminosities in 5 bands, stellar masses, galaxy morphologies, things like that. And we did this plot. So this is the satellite galaxy luminosity function for the Milky Way system. As we observe this in our simulation now, you see, Kasia observed. I mean, this is virtual observation, but now we try to do observation. So you see, this is V band magnitude, absolute magnitude. And this is the number of galaxies that you find. It's a cumulative number of galaxies. And these 3 bands here, 3 panels, differs by just the average mass of the host. And this is important because if you look at the dark matter lambda, cold dark matter or lambda warm dark matter models, you will see that more massive halos tend to have more satellites. So you have to compare apples to apples and oranges to oranges. We have some rough limits on how massive our Milky Way halo may be, but we want to distinguish this and see what happens if you change the mass of the halo. And of course, blue and red lines are cocoa warm and cocoa cold. So, okay, and the bands gives you the 1 sigma scatter from the ensemble average. That's why we want to have 50 or 100 objects to be able to see what's the scatter, because in the galaxy formation, you're so deeply in nonlinear regime that just by chance, crossing the orbit change some satellites, so you have to have many representations to account for this stochasticity. And most important, the last pieces to understand this plot is this dashed line. This is from Koposov et al. 2008, which is the Koposov and his group. They took the observed Milky Way satellite system. They took the map of the dust in the local universe, especially Milky Way, the disk and everything, and accounted and created the model of obscuration. Because we don't observe all of the Milky Way satellites, right? Obviously, you cannot see the satellites behind the disk and behind the galaxy center. There are some pieces of the part of the skies when you have more dust, so you wouldn't see dim galaxies. So it's a kind of they build a compensation model of how many satellites we should see if you could see the whole sky in the same quality. So this is the Koposov line. So what you see, first of all, if you ignore the Koposov line, both cold and warm dark matter nearly give the same prediction. It's really sad if you look at this. Both models predict the same number of satellites unless you go to something like -4. Obviously, you have probably no chance, no hope to observing satellite that will have that luminosity, at least not in our lifetime, I think. Interestingly, they diverge here, but all of them are compatible, except maybe this, which you may use separately as argument that Milky Way halo cannot be that massive, even in both models, because it would have too many satellites compared to what we observed. Okay, well, this is the slide you already seen on Wednesday. Why is that? Because in both models it's very hard to make galaxies. So even though one model have a smaller number of the small clamps, the small clamps wouldn't make a satellite galaxy even in cold dark matter. So it's not enough that that one model predicts there should be hundreds of the small halos, and the other model, so this is cold dark matter, and this is warm dark matter. And only the second model just maybe predicts the small. I just plot very small clamps below 10 to the 8 because of the reionization in all the small clamps in cold dark matter wouldn't create the visible galaxy. And so you cannot use this distinction to really test between the models. But okay, someone would say, wait a minute, you use this semi-analytical galaxy formation model that was built without having in mind the small scales. This semi-analytic galaxy formation model was built to recreate the large-scale big galaxy population we observe in the universe. So maybe it doesn't give us the fair representation of the universe. Did I lose my connection? It would seem so. Right. So, and it would be a fair argument because the semi-analytical galaxy formation models. I remember just trying to do their best to model all the physics but they need lots of calibration, and they were not calibrated that precisely on warm dark matter simulation, so maybe they're missing something. So what we did, we went to another way to approach the problem. We took what we back then could and what was the state-of-the-art hydrodynamical simulation galaxy formation model. It was EAGLE simulations, the EAGLE project. These simulations try to self-consistently model as they progress and evolve dark matter, baryons, and stars and black holes, all this very important physics, gas hydrodynamics, electron cooling, chemical enrichment, star formation, supernovae feedback, supermassive black hole formation, well, there's a supermassive black hole in the Milky Way, right? AGN feedback, well, we don't know, Milky Way probably wasn't AGN, but it had some Fermi bubbles, so there was something interesting, reionization, and so on and so forth. And we applied this. This is just a plot, maybe I don't have that much time, but just to remind you that this important physics will change properties of galaxies as they form stars, and then maybe change prediction of how many satellites the warm and cold dark matter should have. So let me just skip that. Then we implemented this in something was called Apostle project. We wanted to do it in COCO originally, but sometimes politics wins. So Copernicus Complexio simulation, which by the way, if you want to work on it, just come to me and I'll give you all the data we have. It's not public yet, not because of they didn't want it, but we had some problem making it fully public. Nonetheless, Copernicus Complexio shares WMAP7 initial power spectrum. And soon after we ran the simulation, and this was supposed to be the same power spectrum, same initial position as the EAGLE simulation shares. The Planck made a release, there was a slight change, and my boss back then, Carlos Frank, said, oh yeah, Wojtek, Planck solved the cosmology. There's no small h problem. We should move from comoving and just no WMAP, just doing Planck all the time. So we're going to change the initial conditions for EAGLE. But because of that, we couldn't run again the Copernicus Complexio with the hydrodynamics. We have to switch. So it's not the same one-to-one comparison. It's a pity. But nonetheless, we came with this project, which is the local group resimulation, Zoom simulation, local group analogs. So you will have a Milky Way dark matter halo and Andromeda dark matter halo, and you do it in hydro. So this is dark matter. This is what the same model predicts when you render stellar light. So the simulation tells you where the stars are created. Of course, statistically, you don't have individual stars. You have 10 to the million solar masses particles. But nonetheless, and by the way, this is something that has come from tidal features. You can render all the stellar particles. So you have some satellites. And then we did the same for the warm dark matter. This is just a picture how assembly of the local group would look like in gas if you would have cold and warm. This is at redshift 8, I think. So you have this interesting filaments, but you might see there's some more clumpiness, some small stuff creating here than here. Oh, it's very encouraging. We can see some differences, not on the large scales. So let's count the satellites. Let's do the same. And we did, and this is what we got. Again, I hope it's not kicking me out. It is. Right, so, apologies, technology, same things happen with supercomputers. Just to tell you an anecdote, whenever I start a new, very big run, I'm really stressful because even though you take weeks sometimes, well, not weeks, a few days to check all the parameters and while you see something in the next session, you submit the job to the queue. Job usually waits like a few days, maybe a week. And it starts in the 1 second. Why? Because there's some simple comma I forget somewhere and it just corrupts. And then, it's so silly. Oh, I wasted a week. Well, the same happens. So, technology is supposed to make our life easier, but not necessarily always. So this is the repeat of the previous plot when we had only dark matter, only simulation, and some galaxies. Now in full hydro. We have cold dark matter and 2 warm dark matter variants. This number is just a Lepman symmetry. Just the idea is that this is much warmer than this. So this means that this is like warm dark matter that is closer to cold dark matter, and this warm dark matter has less small structure. So again, the lines are observed now Milky Way and Andromeda together because we have a simulation for the local group, not just the Milky Way. And first of all, we see, okay, cool, we could falsify maybe for Andromeda this warm model, but we knew this already because we pick up this model as an extra layer to have some kind of a comparison. But these 2 models are quite feasible, and you see, all of them are similarly compatible with the observation. First of all of them produce very similar amount of satellites, now in stellar mass, because we don't have a prediction for the luminosity that easy. And this is very bad news. This tells you that we cannot tell the difference between the dark matter, warm and cold candidates by just counting the satellites, because all of them, as far as we're concerned, predict the same number of satellites. So this would be empty. You would think, okay, well, no, because we can try to do other things, right? We have the simulation and let's try to be smart. We published one paper. It was kind of a negative result, but it's also important because it tells you that you have to try to construct these observables. One way to try to attack this problem would be, that was our initial guess, that we do the next thing, was let's look to the internal properties. Although both models predict maybe the same amount of satellites, but because the formation histories are different, the amount of the accretion of this dark matter, small clumps, is different, so maybe internal properties of these satellites will be different. And we try to look that. This is Vmax Airmax plot. Vmax is just the maximum of the velocity rotation curve. So, right, if you have this, right, so this is the velocity rotation curve that just corresponds to the enclosed mass potential. You have R versus V. Usually it looks something like that, right? So you have a maximum of velocity and then you move away, there's not much matter contributing, so, well, of course, maybe something like that. So there's the inner parts of the velocity, you will have something that would more or less look flat if you have a baryonic component, but for the satellites it's not so simple. Anyway, the Vmax is this point. So Airmax, Vmax is just the location of this peak of the circular velocity diagram of an internal stars, gas and matter composition of a satellite. So we did this plot, Vmax, Airmax, and it tells you the relation of the Vmax to Airmax tells you that how compact is the satellite. Because if this takes the Vmax if you have a curve like that for the same or less enclosed mass gets the smaller Airmax, it means it's more condensed in the center. It has much more matter in the center, more dense. It's for the same enclosed mass. You take the Airmax at the same Vmax as at larger radii, it means you are less condensed, less compact. And there are some trends that will tell you that the warm dark matter satellites tend to be less compact because the Airmaxes are higher. But if you look at the scatter, this is isolated galaxies and this is satellite galaxies. For isolated, maybe you could get some trends. But for satellite galaxies, the scatter is big. So it's okay. This might look a bit hopeless because there are some slight differences, but it would seem that the variation induced by the stochastic process of the satellite formation and survival brings much more to this than just it erases some of this internal physics. So even though they should differ, it will be very, very hard to observe this in reality. So this is the next thing we wanted to do, and actually this is going to be, I think, positive story ending this part of the lecture. When we found something interesting, and at the very end of this presentation, I will try to convince you that soon enough, during our lifetime, and I mean really like in a few years, when LSST finally launches, we should be able to falsify one of these models with a high sigma significance. How? Well, we turn something that appeared to be disadvantage into advantage. So this is the plot that inspired us to model what I mean here. So I told you before that one model predicts many more of the small clumps, but they're actually invisible than the other model, right? This model predicts dark halos, if you like, or dark satellites. Small clumps that never succeed to make a galaxy. And this is some kind of a difference. And how we could observe that? Well, in a moment. First of all, we went to the hydro simulation with the cold dark matter and two versions of the warm dark matter. And we took every line, every pair of lines, gray and black, is coming from the one Milky Way system now. And thick black lines are the satellites, the halos that had some satellites, had some galaxy inside, so had some stellar particles, should be in principle visible, luminous. And the gray lines are all these dark halos. So first of all, you see that all models have dark halos, also in warm dark matter, but there are many, many fewer of these dark halos. And this model, a particular small halo, let's say at around 50 kilometers per second Vmax or 10 kilometers per second Vmax, predicts factor of 20 more, because here you have around 20 dark halos prediction, and here you have over the 100. So it's interesting. So one model prediction should be nearly order of 100 more dark halos than the visible one. Well, how you could test it? Let's go back to amazing general relativity and lensing. This time we'll need strong lensing. We need small scale, very strong magnification and deviations of the light. So again, we need to look for a system when you have some faraway galaxy, and at best, exactly in the middle, there should be some strong gravitational lens, because if it's exactly in the middle by just construction of the geometry, you get the strongest lensing effect. And ideally, you would like to find something like that, Einstein ring. So this is very massive elliptical galaxy, which is lens, and then you have a lens faraway high redshift galaxy, which is smeared out along the Einstein radius. Why you need this? Because when you're close to Einstein radius, you start to be close to the caustic-like behavior of the lensing plane, which means the small variation in the mass distribution here will make a big impact of how light rays travel. So if you happen to hit some of the dark halos here, they should change the properties of this distorted image if there wouldn't be any dark halos. And going back to the Copernicus complexio, and now we're doing this not just calculation in the Apostle, which is only 6. Apostle, we only had 6 Milky Ways. In Copernicus complexio, we have around 100, so we can do good statistics. This is satellite subhalo mass function. So this is the power spectrum. Forget about that. Again, how many objects of this mass you should expect? One model is black. This is 10, and this is bracketing of the mass of the host. And this is cold dark matter, this is warm dark matter. So we can use this difference to predict how many halos like that should be in the lensing system like that. And this is what we did. This is a complicated slide, but I will try to walk you through it. What's essential is that you can go to simulation, extract halos of massive elliptical galaxies like 10 to the 12, 10 to the 13, depends on the redshift, and basically found this distribution of satellites. And you should know, and you can do exactly the same objects in warm and cold dark matter simulation, because we started all of them with the same initial phases. So you can know, you can minimize the scattering. We just tell you, okay, if the lens would be here in this galaxy, and this galaxy has, 100 times more, and we know where they are, how far they are from the center of the halo, we have the way to put the very simple massive elliptical galaxy model inside of our halo, and we can do the lensing, mock lensing observations. Mock Kasha observations. Very good. Sorry. So, and what we could get was the following. So, MC is the halo cutoff mass. It's just effective mass below which you start to have so few halos that they no longer have a subhalos. So they no longer have an impact on your lensing statistics. So this is MC. And this is the kind of a surface total limit on the Einstein radius. The idea is that, let's say, we have a minimum halo mass around 10 to the 8, right? This means that, if there's a real cold dark matter, we try to measure this MC parameter from our analysis. So we analyze the lensing system and see, okay, if there would be some kind of a universal threshold in our universe, below which you really suppressed amount of small halos, this is this MC, if we could we detect it in the observation? So if we have around 20 systems like that, 20 systems, by the way, when we were writing this paper, we knew 5. So if you have 20 systems like that, you could get this contour levels if the universe were cold, or this detection of the minimum halo mass if the universe was warm. So you see, this is just 1 sigma, maybe 2 sigma deviation. But if you could have hundreds of strong lenses like that, so a factor of 20 more than we know today, then this is what we could do. If the dark matter would be cold, then we would rule out the warm dark matter at many sigma, more than 5 for sure. if you see, this is many, many sigma away from this. But if the dark matter is warm, then we could rule out cold dark matter at 3 sigma. Well, 3 sigma is not great, but it's better than 0 sigma, right? No one really was able to rule out cold dark matter yet. So we created this and show if we can have from 20 up to even 100 systems like with the lensing quality of this, we could detect this minimum halo mass, which means either we would falsify cold dark matter if we detect the minimum halo mass, or we can falsify warm dark matter if we don't detect it on this threshold. So, where's the press release? Well, as I said, it's very, very hard to get these observations in the sky because it's serendipitous to find very strong lens like that exactly nearly halfway to create the Einstein radius. But that's why I would mention with the LSST, a large survey of space and time on the Vera Rubin Observatory, because it will observe all the sky continuously and in a robotic automated way, which is the best way to detect, to just discover objects like that, the lens like that. The prediction, naive prediction, is that we should get to the 50 after like 3 or 4 years of the running of LSST, which means if all of this is not bothery, we should meet at the Cosmology School 12, maybe in 7 years or something, and then I can tell you, oh, we won't be discussing either warm or cold dark matter at all, because it will be falsified observations. So I will leave you with my conclusions here, that falsifying cold and warm dark matter, so we try to do model testing, right? We never can tell if the model is really correct. This is now in physics, because you never know what kind of systematic or important physics you miss. But if your model predicts something that doesn't exist, right? That there's no way you can observe this, then it's a weak argument against the model. But this is a strong argument against the model. But if the model predicts something that is not observed, it's actually a weak argument, because you never know if you're missing the observation because of something. Nonetheless, you can take some simulations, make this kind of a setup, try as much as hard to try to use in hydro or cold dark matter only. It turned out that they can be meaningful, because we found this strong observable that potentially can tell us to differentiate on the phenomenological level which dark matter models we have in our universe, which will be very interesting. It will give a huge boost to the theorists to work on this particular parameter space. And I think what we can also learn that at certain level, when you go to the dwarf galaxies, the physics of the baryons and gas is so dominating that even if you have strong differences in dark matter, like in this case, one model has much more structure than the other, the baryon physics is so dominating that it erases these differences. So you cannot get away with the very good understanding of the galaxy formation if you want to test cosmology on the small scales. Thanks very much.